Yeah, I'm going to talk about LambdaCube 3D, and as it was introduced, it's a purely functional API for GPU graphics. And this is my spare time research project, essentially. So the idea, the main intention behind this project is to get a better graphics programming experience by providing tools for the programmer to create less errors and could also do more code reuse while keeping the same performance. The idea is to try to automate the engine coders' work as much as possible with a tool and let the system to do the elaboration of the technical details. Obviously, this is a trade-off, but anyway, that's the intention, and the methods are I borrowed from functional programming. So the idea is to let the programmer to give a higher level description of the graphics pipeline, like I choose to as a data flow pipeline description, and also because the TIS tool can observe the whole 3D engine at once, it can validate each stages, like whether certain API, GPU API constraints are held, or whether the inputs and outputs are compatible with each other in certain stages. So normally or usually the graphics programming is done in imperative way because the full control of the people want full control of performance, which is acceptable, but anyway, this is a research project, so anyway. Looks complicated, and yeah, we know this. So there are a lot of instructions here, but essentially this boils down to three categories, like either it's a resource allocation, or which deals with data uploading to GPU, or draw state configuration, enabling or disabling some GPU features, and the draw calls. But I think it's possible to extract a high-level description. Like we can see the GPU hardware as a stream processor where we have different stages and is gradually processed data. Like if you want to render a triangle, then we initiate the data from a buffer, and the vertex shader will be applied and transform it to something else. Then the rasterizer will fill the triangles and so forth and so on. So the idea is to capture this stream processing property and introduce primitive operations just to model these stages and use these stream transformers to describe this pipeline and compose them together. That would give the higher level description. So the problem here is, or one problem which needs to be solved, that OpenGL API is stateful. The state is the GPU configuration, which describes the enabled features and the buffers. But we use a stateful API to change this, to alter this configuration. But this configuration essentially is relevant for certain stages of the pipeline execution. So it uses pieces of information from this configuration. So we can extract this information and put it into a data structure. I'll call it rasterization context and accumulation context. That's the state which is relevant to the stage. So that's how we can turn a stateful API into a pure one. And if we do this, we will discover that our graphics pipeline become a purely mathematical function without side effects, because every relevant data it gets, it's an argument, and the result depends only from the argument. So if we have a texture mapping pipeline, we should provide the geometry, the texture, the camera matrix, and an empty frame buffer just to produce the result image. And if we provide the same input, it always gets the same output. So that's the idea of this behind this approach. So LambdaCube 3D is an implementation of this approach. It's a Haskell-like language. It has its own compiler, and if we want to use it, we have to describe the graphics the whole graphics pipeline, the engine essentially, in this language, and we should choose a backend for our application. So the compiler will compile this declarative and purely functional description into an intermediate representation, which will be executed by a backend. I have backends for desktop and web and for mobile, but those are experimental. So the backend API has a special. The backend has an API to feed the data into the pipeline, and it's typed. But we will see it later. Okay. So let's see some code at work. So the project has a web page. You can find more information, and also has an online editor, which you can see the preview window and the text, the source code editor. It also shows the types of values. So this is a Haskell-like language. It has type inference. It's extreme. I went extreme, I admit, because this is the absolutely purely functional approach of this problem. But anyway, I just wanted to discover. So if we do animation, then time should be a parameter for our rendering function, and we can adjust the time in the editor. So this is the toy thing. The simplest thing what we can do is a clean screen. Every LambdaCube function should have a main function. Every LambdaCube program should have a main function where we specify the frame buffer which need to be put to the screen. So this one is an empty one, which consists of a clean image filled with a single color. We can change this color, and the live coding, just fast forward there, will update the preview window, and we can change it back. So the next thing, which will eventually involve some rasterizer thing here, is a textured cube. It also has the main function but this time the frame buffer is not a constant. It's produced using a function, and we have to provide the stream data and the uniform data into it. And actually, we have to provide an interface between our graphics pipeline and the application. And this time, stream, and position, and so everything what's in code, I call it slots. They are names what the pipeline description can refer to, and also the application. And those have types. We can see the types in the top. So time is float. The stream is a triangle stream with two vertex attributes. One is 4-dimensional, the other is 2-dimensional because it's for the texture coordinates. And we will use this data in our pipeline description. The frame buffer is composed from two things. The empty frame buffer, like the image frame, is the background essentially, and the render stuff, which is the fragments. And we can change the background color, the whatever. So we've seen this. Then, to understand what's going on during the rasterization, let's check the code. So obviously for projection we need to use a projection matrix, which is composed from the usual stuff, the projection matrix, look-at matrix, and the rotation. Maybe you're not familiar with this syntax. This is Haskell syntax, and the order of things doesn't matter. It's only data dependency what actually matters. So this proimat is used in the fragments. So there, the fragments value is a frame buffer, and it's the result of a stream transformation chain. And this AND operator is its inverse function composition. That means we take a vertex stream, we transform it through a vertex shader, which is the parameter of the map primitives, and we rasterize it. Then we map the fragment shader using the map fragments, and we turn the fragments into the final colors, and with the accumulate width gives the configuration for the pixel operation stage, like the Z buffer operations and the blending. We can change the, that's where the promat is used in the vertex shader. That function, I go back. So it's an anonymous function. It's a lambda function, and the system compiles to GLSL and OpenGL operations, but that's the low-level part. So the sampler will be used in the fragment shader to do the actual texture lookup, and it also has the name which needs to be filled by the application. So that texture slot is that's where the texture data is fed into it. Okay. That's the rasterization. That line is which does the rasterization, and that's the one which is the fragment shader. Okay, let's modify. If we modify the fragment shader, like we could add an offset to the texture coordinate, and the system will derive the new pipeline implementation. So this live coding concept is good for experimenting with algorithms and effects. And the difference between a shader language and LambdaCube is that LambdaCube is a multipass algorithm can be expressed in this language because it's not only shader, it involves the draw calls and the whole graphics pipeline. The other thing which is interesting and useful is that it's typed, and it's functional languages like Haskell have more advanced type systems than imperative languages usually. And it is possible in an advanced type system to encode API constraints, essentially specifications at type level. Like in the case of LambdaCube, I managed to encode the OpenGL specification, the constraints and types. So if it type checks, that means our pipeline is correct. But that's a design choice. It's up to the developer who designs the language whether he wants to check everything or just the most important things, because obviously too detailed types can overcomplicate things. So the right balance should be found. So let's check an example how let's make a mistake. Change the two-dimensional float vector to a three-dimensional one, and the system will eventually find where it causes an error. Like it will cause an error because our texture lookup function expects a two-dimensional vector for the texture coordinate instead of a three-dimensional vector. Okay, let's maybe. So that was the case when our stream was incompatible with our pipeline. But it's also possible when our vertex shader is not compatible. The output is not compatible with the fragment shader input. Like here, when we try to pass the input vector, the four-dimensional vector as a texture coordinate, as an input for the fragment shader, then it will cause an error also. But for example, if we use Swizzling, I mean, we can fix this. That's obviously useless, but anyway, we can turn a four-dimensional vector to a two-dimensional one, and eventually it'll be fine. Okay, let's check a more interesting example. So we have a language where we can describe declaratively the whole pipeline with functions, and we can use functional composition. And we've seen the textured cube. What if we give a generic textured cube algorithm, and we pass the texture what we want to put in the side of the cube as a parameter. This is an example for this, where so this cube prime is essentially very similar to the previous example, but it has this FB frame buffer parameter, which will be used as a texture, render texture, the source texture for this sampler, and so this frame buffer will be put to the side of the cube. And the other trick here, what's going on, is the iterate creates an infinite list lazily, where the first element of the list is the blank screen, and the first one is a cube rendered, where the previous frame is rendered, where the previous item of the list is rendered to the cube. So the first one is a blank screen. The second item of that list is a blank screen cube on top of it. The second one is a cube in cube. The third is cube in cube in cube. Whatever. The point is, I could easily compose this weird concept in this code. The task system ensures that I don't mess up, and I just adjust this thing as a parameter, and the compiler will derive the resource description and the draw calls instruction sequence from this description. So the point here is to prove that this would be more complicated to do it by hand, basically. Okay. All right. The other example what I want to show is also for composition. Let's say we want to, this is another example in our web page. Let's try to put this on this textured cube. Here we have to import these two modules, and we will reuse the functions from those modules. One is this make frame, the other is cube prime. And we use the same trick here. And so this is the proof of concept that code reuse is easier here. Okay. Anyway, it's a useless example, but I guess it proves the concept. Another example is a ambient occlusion field, but I just put it here because it looks nice. So I don't want to go into details here. Right. The last, not the last. The another example, what I want to show is a Haskell game. It's a tiny program with almost 600 lines of code, including the pipeline. It's a simple version of asteroids. So the application is implemented in Haskell. The graphics is implemented in LambdaCube, and the cool thing here is that we can reload the whole graphics pipeline, the 3D engine, on the fly without restarting the application. So this facilitates experimenting with effects or application. So, for example, now the collision geometry, which is the wireframe stuff, is enabled. That rendering, this application renders the collision geometry. But if I just change the corresponding part of the pipeline to, like, if I comment it out, it immediately reloads recompiles the pipeline and replaces the old one with the new one. Also can enable some other parts of the pipeline, like do some post-processing here. So the thing is that the 3D engine is separated from the application. The interactive part of the application is in our chosen language, and graphics is described as a pure function, and we can combine them together. All right, the last example what I would like to show is a bigger one, which exists because I wanted to make sure that this scales to a bigger thing. So it's a re-implementation of a Quake 3 map. It's a Quake 3 map viewer, and it uses the demo content of the original game. The whole pipeline is described in LambdaCube in a pure functional way, and It also can swap the pipeline on the fly. It has a debug pipeline with the collision geometry rendered and the normal one. So, okay, I think the takeaway of this is it is possible to describe the graphics in a high-level way, like in case of LambdaCube, it's a purely functional way, using declarative description and having a tool doing compile time validation, and the functional approach facilitates code reuse. And so that's my conclusion. But this is not finished, so you can ask whether it's how does it perform. It's not everything is squeezed, but anyway, we can discuss this after the presentation. Thank you.
Great work. Your LambdaCube code is actual Haskell code?
No.
It's your own code?
Yes. The syntax is deliberately chosen to use Haskell syntax because I have no problem with that. I just had to extend it, like the vector swizzling is a syntax extension. So that's why I didn't use the Haskell compiler.
So you implemented your own type system, which is capable of tracking
yes, it's a
vector.
It's a dependently typed system. Yeah? Yes.
Great.
We need to move on. Further questions delayed to the coffee break. So thanks, Csaba.
Okay.